Assalamualaikum warahmatullahi wabarakatuh and a very good day. We are from Group 1 and we are going to continue our presentation on production of hydrogen peroxide. So for this presentation, we will be covering three aspects which are equipment design, costing estimation with cap cost verification, and profitability analysis. So first and foremost, I am going to introduce our group members. We have Nurul Hidayah, Nur Hani Nabila, me myself, Ainin Sofia, Hanania Rifka, and Muhammad Izwan Helmi. So to jumpstart the presentation, we will start with equipment design. As shown in this slide, it illustrated the process flow diagram of hydrogen peroxide production based on anthraquinone process. So as can be seen here, we have two reactors followed by two towers which are liquid-liquid extractor and distillation column. Then we have separators. And as for the other equipments, we have dryer, mixer, heat exchangers, and pumps. So firstly, I am going to explain about the heuristic of reactor. So the reactor that we have chosen for the process is trickle bed reactor. So it is a catalytic reactor. So based on table 11.17 heuristic for reactor, we follow rule 1, rule 2 and rule 8. So based on these rules, we have evaluated our residence time based on our literature review. And it was found that the residence time of trickle bed reactor is within the range of 1.2 to 6.5 minutes. So the most suitable residence time that we have assumed based on that range would be 3.5 minutes. So we multiply that value and with the volumetric flow rate. But beforehand, we convert it into hours, then we can multiply it with the volumetric flow rate. So the volume of reactor resulted would be 42.1453 meter cube. And as for to determine the diameter of the reactor, based on our literature review, we have found the ratio of height to diameter. So the height would be 5 times of the diameter of reactor. So we use the formula of volume and substitute back the value of volume that we have calculated earlier into that formula, and we determine the value of diameter to be 2.2058 meter. And afterwards, we substitute that value of diameter into 5 times of diameter, and we get the value of height of the reactor to be 11.029 meter.
So next is the major process in this production is oxidator, where in this oxidator process, the process that occurs is the gas liquid process, gas liquid phase. So therefore, we use the bubble column reactor. So based on the heuristic from table 11.17, we use two rules, which is rule number 1 and rule number 8. So for the rule number 1, we use the rate of reaction is in every instance must be established in the laboratory, and the resident time of space velocity and product distribution eventually must be found from a pilot plant. So, and then the next rule, which is the rule number 8, which is the tubular flow reactor are suited to high production at short resident time, second and minute, and when sufficient heat transfer is needed. So based on our literature review, we estimate the resident time and also the ratio of height. So for the resident time, we obtain from the literature review, which is 30 seconds, where we convert this second to hour, and then we can obtain the volume of the reactor. So the value of the reactor we obtain is a 29 meter cube, and for the diameter is about 2.33 meter. And as I say that we find the height is the ratio of height is about 3 times with the diameter. And then we found that the height is about 6 meter. Next.
Okay, for the distillation column heuristic, okay, for the average volatility, which is applied the rule 2 from table 11.13, we obtain is 2.5. From rule 7, table 11.13, for the N minimum is 4.94. From rule 6, also from table 11.13, which is the 9.88. Then from rule 4, 11.14, and rule 9, 11.13, obtained is for the N actual obtained is 19 trace. Okay, from the rule at 11.9 at 11.13, the R minimum obtained is 1.77. From rule 5, 11.13, the R optimum obtained is in range between 2.12 to 2.66. Okay, from rule 2, from 11.14, we can obtain the volumetric flow rate. Then we can calculate the diameter of tower, which in range 0.9 to 0.8 meter. And we have chosen the 0.9 meter for the diameter of tower. From rule 13, 11.13, the length obtained is 14.4 meter. Okay, from the diameter of tower and length of tower, we can calculate the volume of tower, which is 9.1609 meter cube. Okay, from rule 14, 11.13, the ratio we obtain from the length over diameter is less than 30, which is acceptable value. Okay, from the rule 3, table 11.13, which we obtain for the pressure drop for tower is 0.13 bar.
Now, moving on to the next equipment, which is the separator vessel. So there are 5 rules applied for this equipment, which is Rule 3, Rule 4, Rule 5, Rule 9, and lastly Rule 12. So firstly, Rule 3 was applied for this equipment is because gas-liquid phase separator are often designed in vertical position. And then moving on to Rule 9. From Rule 9, we can obtain the value of utilization factor from the equation given in the rule, which is a square root of density of liquid over density of vapor minus 1 by using the value of K without mesh detrainer. And then by obtaining the value of utilization factor, we can obtain the value of the actual utilization factor by using Rule 12 by applying 75%, multiplying it with the utilization factor. So after obtaining the value of the actual utilization factor, we can obtain the value of diameter for the equipment, which is 2.345 meter. So after evaluating the value of the diameter, we can apply Rule 5, which is the hold up time 5 minutes, by multiplying it with the volume to obtain the value of the length of the equipment. So as we have calculated the value of the length of the equipment, it is found that the ratio of length to diameter is out of range. So therefore, by applying Rule 4, 2.5 diameter is multiplied with the 2.5 is multiplied with diameter, so we have obtained the value of the new length for the equipment, which is 3.0725 meter. And lastly is to obtain the value of the volume for the vessel by applying the formula of pi r square L. In substituting the value of length and diameter, we obtain for the volume of the vessel is 13.331 meter cube.
So next, separator vessel 2. Using the same rule of vessel 1, we calculate the U equal to K square root density liquid over density vapor minus 1. For the K, we use without the mesh detrainer. Then we use the formula volume of liquid 0.5 L pi D square over 4. We found the D, which is 1.0923 meter. So L equal to 2.9308. For the volume, we use cylindrical volume, which is pi r square L, and the V is 10 meter cube. So next is heat exchanger. So we use heuristic of rule 1, 3, 6, 7, and 8. So first of all, we need to find the delta TLM. So we use the cooler, which is the temperature is 120 to 100, and then the delta TLM is 8.82 degrees C. And then the Q that we calculated from the energy balance, we put into the formula, which is Q equal to UAF delta TLM. So we got the A is equal to 1.7764 meter squared.
As for the next other equipment, which is the pump, we will refer to table 11.10 for compressors, fans, blowers, and vacuum pumps. So we follow rule 1 and rule 7. So for rule 1, this is where we use to find the shaft power, which is 1.67 multiplied with our volumetric flow rate in the unit of meter cube per minute. And later we multiply with the delta P divided with the fractional efficiency. So for the fractional efficiency, this is where we utilize rule number 7. The efficiency is at 70%. So when we substitute all the values, we will get the shaft power to be 0.5086 kilowatt.
Next, moving on to the next part of the presentation, which is the costing calculation with cap cost verification. So firstly, we have managed to calculate our bare module cost for each of our equipment. So these are one of the sample calculation for our equipment, which is the separator vessel. So firstly, we have to obtain the value of the respective K1, K2, K3 from table A1. And then we have to substitute the value of the respective K into the formula of log 10 Cp naught to obtain the value of Cp naught. So we have obtained the value of 1373.96 for the Cp naught. Then moving on, to calculate the bare module cost, we have to obtain the value of Fp and Fm. So for Fp, we have calculated the value by using the formula shown in the slide. And as for Fm, we have to obtain the value of Fm by evaluating the equipment based on their specific criteria, which is the material of construction, identification number, and so on. So after obtaining both of the values, we can calculate the CBM for separator, which is at 6614.56, and then the value for the equipment for 2023 is 174,261.5533. So these are the summarized table for our CBM for all equipments, including major and side equipments. So for the SEPC, we have used the year of 2001 as our best year, and followed by the current year, which is 2023.
So next, for the cost of manufacturing, first of all is cost of raw material. For our raw material, we use 2-ethyl anthraquinone and hydrogen. Price of raw material for 2-ethyl anthraquinone is $27 per ton, and then $238 for hydrogen per ton. So total cost of raw material is $19 million. Okay, so for the cost of utilities, we have two types of utilities, which is pump and heat exchanger. So for pump, we have 4 pumps. We calculate the shaft power by using the heuristic, and then we use this formula and also stream factor of 1.9726 to calculate the electric drive. For electric power, we use shaft power divided by electric drive, and then we got the total cost of pump is $7,000. So next is heat exchanger. We have 3 coolers and 1 heater. So for the utility cost of heat exchanger is $149. So the total utility cost is $8,000.
So to verify the findings that we have obtained, here is the cap cost verification that we have run by using cap cost simulation. So for the utilities that we have obtained from the cap cost is roughly around 7,000 compared to the utilities cost that we have done by manual calculation, which is at $1,000.
So for the cost of waste treatment, we use palladium as our catalyst, and we need to treat this catalyst once a year. So the price treatment is $0.6 per kg. So total cost of waste treatment is $97,000. So for the cost of labors, we decided to operate the plant for 51 weeks and 5 shifts per week. That means we got 3 shifts per day and 5 operators per shift. So for a day, we got 15 operators. To use the formula of NOL, we have to find NNP, which is the sum of equipments which are reactor, heat exchanger, tower equal to 7. Then the NOL is 2.8107 times to 5 operators. We got NOP, which is 15 operators per day. So based on the journal, this is our salary per month and per year for N operator. So the cost of labor is $29,000. To find the total cost of manufacturing, we use the COM and COMD formula, which mean cost of manufacturing with and without depreciation. So for the COM, we got $25734,274 and COMD $25254,877.
Therefore, by comparing the manual calculation with the cap cost verification, here we can see that the value that we have obtained for the cost of manufacturing without depreciation is around $25 million. Comparing it to the manual calculation, which is pretty similar, $25 million as well.
Okay, next is total module cost and grassroots cost. So these two costs is important for our plan to estimate the total capital cost. So the total module cost for this production is 2,880,793. And for the CGR, which is the grassroots cost, we use the equation of total module cost plus with 0.5 multiple with the total by module cost node, and hence we got the CGR value is about $4,060,487. This CGR is equal to the fixed capital investment. Then we next. Then we verify our calculation with the cap cost, which is as is shown in this slide. It shows that the cap cost value for the total module cost is about $3,810, and for the total grass cost is $4,680,000. Where the one that we calculate for the total module cost is about 2,880,000, and for the CGR is a 4 million. So this show that have no significant difference with our calculation. Therefore, this value is acceptable. Next. Next, we go to the revenue and working capital. So the revenue, since our product is only hydrogen peroxide, so the price per ton is the price for hydrogen is about $615 per ton, and for per year we calculated the price is about 39,309,077 per year. And for the working capital, so the working capital, we use this equation, which is 0.15 multiple with the fixed capital investment, and the value that we get is for the working capital is 600 and 609,073. Next, we go to the land cost. So, our plant location is at Panvel, Mumbai, India, where the area is about 19 acres, and it shows that the total cost for this area is about 351,401.
Next, moving on to the profitability analysis. First, we will be covering on the non-discounted cash flow. In order for us to produce the non-discounted cash flow diagram and also table, we have listed out all the cost estimation that we have evaluated earlier, which consists of land, fixed capital investment, working capital, revenue, cost of manufacturing, land plus working capital. And aside from that, we also have evaluated the percentage of which the fixed capital investment will be fully finished paid. So aside from that, we have also evaluated the depreciation allowance based on marks method, based on textbook for 5 years. As can be seen in this slide, from year 1, the depreciation allowance is 20%, year 2, it will be 32%, year 3 is 19.2%, year 4 and 5 is 11.52%. As for the depreciation straight line, we use this formula of fixed capital investment subtracted with the salvage value, which we assume it to be 0, and divided it with our project life, which is 10. And in that table, it shows the depreciation straight line values from year 1 until year 6. And aside from that, we have determined that taxation rate for this production to be 30% alongside with the construction period to be 3 years. Based on this slide, it shows the non-discounted cash flow table. So the first column representing the end of year K, starting from year 0 until year 13. So year 0 until year 3 representing the construction period, and year 4 is where the project started until year 13. And the next column stands for the investment that we have listed out before, alongside with the third column stands for the depreciation straight line that we have calculated using marks method for year 4 until year 9. Then afterwards, we subtract the fixed capital investment with the depreciation, and we got the value as shown in the table. Then as for the revenue and cost of manufacturing, it will retain the same from year 4 until year 13. And as for the next column is where the revenue is subtracted with the cost of manufacturing and depreciation and multiplied with 1 minus with the taxation rate and later plus with the depreciation. And as for the cash flow, we will got it as shown in the table. And lastly, the cumulative cash flow is where we add up the cash flow diagonally. And as per illustrated on this slide, it shows the non-discounted cash flow based on the table before. So it can be seen that the slope of the non-discounted cash flow to be 8 power of 6. And we have indicated the land cost at year 0 to be $8,000 for the fixed capital investment to be paid after the construction period at $4 million, and for the fixed capital investment to be fully finished paid for the payback period with 3.53 years. And as can be seen here, the cumulative cash position is located at the 13th year, which resulted to be $96 million. And based on the the non-discounted cash flow diagram before, this is how we calculate the payback period. So the payback period is where the land cost will be add up with the working capital cost. So the payback period cumulative cash flow is in between year 3 cumulative cash flow and year 4. So this is where we must utilize interpolation by key in all the values that is illustrated in the table, and we will get the payback period to be 3.53 years. So moving on to the cumulative cash position. Cumulative cash position stands for the final value of cumulative cash flow that we have constructed before. So the value would be $96 million, $96,000 million. And as for the cumulative cash ratio, we use the formula of summation of positive cash flow divided with summation of negative cash flow. And we got the value of CCR to be 22.79 to 1. Lastly, would be the rate of return on investment, ROROI. So this is the formula that we use to find ROROI, which is the slope 8 power of 6 divided with $4 million, which is our fixed capital investment, subtracted it with 1 divided with our project life, which is 10, and resulted to be 187%. So this is the cap cost verification on the non-discounted cash flow. As you can see here, the big cash flow diagram for non-discounted is verified from the cap cost. It can be seen that the trend, the shape, and the slope is similar to the manual interpretation of the cash flow diagram. And this is where we have compared the cumulative cash position, ROROI, and payback period from the cap cost and the manual calculation. So as can be seen, the CCP value from cap cost is 96.39 million, whereas our CCP manual calculation is $96 million. As for ROROI, it is 237%, and our ROROI is 187%. And as for the payback period, it's 3.5 years for cap cost, and our payback period is 3.53 years. So it could be summarized that although it has slight differences in the cap cost and manual calculation, but the value is still acceptable.
Okay, for the discounted cash flow, from non-discounted cash flow, we use the 2% of discount factor to calculate the discounted cash flow. Therefore, we can obtain the new cumulative cash flow, which is the cumulative discounted cash flow. Okay. Okay, from this is the discounted cash flow diagram, which can be seen that the land cost is at 0 year is 351,000, and for the fixed capital investment is 4 million, and for the discounted payback period is 3.56 years. Then the net present value, which is the final value for the cumulative discounted cash flow, is 80 million. Okay, for the discounted payback period, the discount payback period is in between year 3 and year 4, at which the cumulative cash flow is the total cost of land plus working capital, which is 960,000 dollar. Okay. For then we obtain the discounted payback period is 3.56 years. Okay. The net present value, which is the final value of the cumulative discounted cash flow, which is 80 million. Okay, for the present value ratio, is the summation of positive cash flow over summation of negative cash flow. Then we obtain the present value ratio is 20.0378. Next. Okay, for the discounted cash flow rate of return DCFRR, DCFRR is at which the NPV is at 0. So we use the trial and error method, which the NPV equal to 0 is in between the discounted factor of 90% to 100%. So then we use the interpolation method to calculate the DCFRR, which we obtain is 92.44%. Okay, for the cap cost verification, we can see that the cap cost and the manual interpretation is nearly similar. Okay. Okay, for the from the cap cost calculation, which for the net present value, which is 81 million, discount and for the discounted cash flow rate of return is 89.71%, and discount payback period for the cap cost is 3.9 years. Whereas for the manual calculation, we obtain that for the net present value is 80 million. For the discounted cash flow rate of return is 92%. Then for the discounted payback period is 3.56 years. So to summarize, it have the slight difference between the two calculation. To summarize, we have verified the manual calculation that we have obtained. Although a slight difference was found, but we assume that all of the values are acceptable. Okay, for the cap cost verification, we can see that the cap cost and the manual interpretation is nearly similar. Okay. Okay, for the from the cap cost calculation, which for the net present value, which is 81 million, discount and for the discounted cash flow rate of return is 89.71%, and discount payback period for the cap cost is 3.9 years. Whereas for the manual calculation, we obtain that for the net present value is 80 million. For the discounted cash flow rate of return is 92%. Then for the discounted payback period is 3.56 years. So to summarize, it have the slight difference between the two calculation. To summarize, we have verified the manual calculation that we have obtained. Although a slight difference was found, but we assume that all of the values are acceptable.